first topic on waves, and it covers a simple idea of reflection. That's simple, but has some rather complicated consequences that we need to become familiar with. So let's just remind ourselves of what happens to light. So here is our mirror, which is the easiest thing for reflections to take place on. And light travels as a ray. So light travels as a ray in a straight line. That's important. And it shows the direction in which the light goes. Of course, if you wanted to draw, say, the crests of these transverse waves, because we know it's a transverse wave, we could draw that. However, it then, but it does travel in a straight line, we know that for sure. And then we know, from experience I hope, that we have a reflection that takes place when the ray of light comes back out. And if we want to, again, we can draw in the crests of the wave. Now bearing in mind those crests, those are the tops of the waves, they should be regularly spaced all the way along. Now this is different from, say, a rough surface. So if that were a rough surface and a ray of light were coming in, it would get reflected at a lot of strange angles. And it wouldn't all behave like it does in this ideal situation. So this light is an example of scattered light. And that's off a rough or a matte surface. However, in this instance we have a nice plane mirror which gives a nice perfect reflection. And there's a simple rule which we need to bear in mind, which I'm sure you're familiar with. That says the angle of incidence i.e. the incoming ray equals the angle of reflection. However, one thing that people often get wrong is that they wonder what angle and what position you're measuring it from. And often they do it in this gap here. But we must make reference to this line, this dotted line, and we call this dotted line the normal. How do we know what the normal is? Well, the normal is at 90 degrees to the surface, or in this case, the mirror. So in other words, it's at 90 degrees. And then we measure our incoming angle of incidence from that reference and the angle of reflection from that reference. So therefore we can say that theta angles, theta r, angle of incidence is equal to the angle of reflection. So I hope that makes good sense. We could have another mirror here, for instance, and we'd get the same effect happening, where the angle of incidence, this time it's the second one, should equal the angle of reflection, it's the second one. And that bounces back and forth and so on and so forth. Now there is quite an interesting use, I'd say interesting, or one which they might examine you on, and that is a periscope. A periscope is either used in submarines or they were used in the First World War in the trenches to see around a corner or to see over a bump in the First World War at the trenches, or to see up above the ocean. And what happens is this column allows light to strike a mirror, then it travels up to strike the other mirror, and then it moves on around the obstacle. So I suppose you are seeing light pouring in to your eye. We'll use that type of symbol for an eye. And here are the two mirrors. Now I suppose the question is, what angle does this need to be at? Or what angle does the mirror need to be at in order for that effect to occur? And I hope you know that if this entire angle is 90 degrees, the angle of incidence must be 45 and the angle of reflection must be 45. And that process is repeated. degrees, degrees, degrees. Excellent. So once again, quite a simple law, but we need to bear in mind its consequences. I suppose I should say here as well that this doesn't just mean one angle. If I stepped up the angle to a very, very steep angle, then we'd get a very, very steep angle occurring as our angle of reflection. Okay, now it's not just we don't just need to bear that law in mind. We need to be able to draw ray diagrams of what's happening. A little bit like this, but a bit more complicated because we need to work out how an image would form. But before we get to that point, let's just look at the periscope again, and let's think what would happen if, drawing my periscope, what would happen if we had something like a fly stuck in the periscope? And let's imagine that the fly, or this object, let's just call it a triangle. Actually, that's my best attempt to the fly. And let's imagine that the light was pouring in, but the fly chose to move this way. And your eye is here. Where would you see the fly move? Well, let's just imagine in its stationary position. You see the fly like that. If the fly moves that way, then it actually moves up with regards to your eye. You could imagine that because if it were in this position here, angle of reflection would be over there. What happens if the fly were to move nearer the secondary mirror? What would happen then? Well, it's moving away. It's not actually moving in position, but it is moving away from you. And finally, what would happen if it moved this way? Well, if it were moving that way, then the reflected beam would be lower. Hope you can see that. So bear that in mind. Once again, the reason why this topic is regarded as complicated is you have to try and think three-dimensionally what's happening with terms of images, because after all you are seeing the image of the fly and its position. Great. Okay, let's turn to images formed in mirrors now. I'm going to place the mirror much more simply just here. This is the back of the mirror. I'll draw it very faintly because I need to draw behind there, so that's very faint. And I'm going to draw a dot there. Here is my eye. Now, where do I see the dot in the mirror? Well, let's just, once again, use our angle of incidence equals angle of reflection next to our normal, which is drawn in, remember, at 90 degrees to the surface. However, our eyes like to see or assume that light has travelled in a straight line. It doesn't really understand that light has actually been reflected. So what happens is it imagines that the light has come from somewhere in a straight line. Somewhere over here. Where this is the object, this is the image that is seen. It's not really there. It doesn't really exist behind the mirror, but you see it as behind the mirror. Imagine every time you look in the mirror, it looks like somebody behind the mirror is looking at you. Interestingly enough as well, that the distance the object is away from the mirror is also the distance that the image is behind the mirror. So that's very important. I suppose the lateral displacement here as well. But the image behind must be the same distance as the image in front, because it's assuming that light travels in a straight line. That's what your eye is assuming. So you see everything behind the mirror, rather than realizing it's bounced off of. If that's not too weird. Okay, but here's our second example. What happens if we don't just have something which is a dot, but we have something which actually has a size and a shape? I'll draw this slightly bigger so it makes life easier. And here is our eye. Okay, now the light from the way that we consider this is, first of all, we take the light from the top, and we appreciate that the angle of incidence must equal the angle of reflection. And then we take the light from the bottom, and we understand the angle of incidence must equal the angle of reflection. It's getting to the same point. Because this angle is going to be slightly larger than this one, because it hasn't covered the same distance. However, what does your eye see? Remember, light travels in a straight line, so your eye does not think it's seen it here. In actual fact, what it thinks it's seen, maybe I'll just draw that a little bit more profoundly, is it with a ruler. This makes much more sense. Maybe I should say that you should do this with a ruler. But what it thinks it's seen is it thinks it's seen the top of the ray coming from this point here, and top of the pin, or the arrow, sorry, and it thinks it's seen the bottom of the arrow coming from this point here, and everything in between. So there we have our image. Again, same distance away as the object is away from the mirror. Okay, let's step that up one more idea. And this time let's place an arrow in, but the arrow is leaning away. And here is my eye again. It's getting ever wider. I don't know whether that's because it's becoming more shocked. The arrow's leaning away. Now, are we expecting the arrow to lean in the same direction with regards to the eye, or to lean away with regards to the eye? Well, let's follow through our rules that we've set up. Okay, let's go from the bottom first. The angle of incidence must equal the angle of reflection. And from the top of the eye, top of the pin, sorry, the angle of incidence must equal the angle of reflection. It must go to the same point. Slightly bigger angle in that instance. Now remember the rule we've set up here. These distances must be equal. Well, so too must these distances from the top and the bottom. So we track this one back, and at the same distance we get the bottom of the pin. We track this one back, and at the same distance we get the top of the pin. I say pin, arrow I should be saying. So here we have the object again with a certain distance. Let's call this one D, and let's call this one A. So there is our distance A, and there is our distance D. Maybe I should draw it in more solidly so you can see what's happening. This one here more solidly, and this one more solidly. Okay, so our object and our image is slanting away. I don't know whether that surprises you at all. But it definitely helps when you consider thinking about how letters are formed. So if I had the letters A, B and C here, and this is where I'm looking at it from, then those same letters will be formed on the other side. However, this time the letters will be formed A in this direction because this bit is closer, hence this bit must be closer. That's further away, that's further away. We have the B facing the opposite direction because this bit is closer, the arm is closer than the far bit. And C, this part must be closer than the other part if the mirror is in that direction. I won't draw in all the individual lines, that will get really complicated. However, this means that we get this effect called lateral inversion. It means that all writing that you'd see in a mirror is back to front. It means when you're looking in the mirror, the left side of your face is really the right side of your face, and vice versa. If I were to think about drawing it as a mirror, like that, an arrow looking that way would look like the arrow were going that way in the image, in the object. So it does the opposite. Okay, some confusing stuff. Now the last bit I want to show you is how we can get some interesting effects. One of them would be what happens if we put two mirrors at right angles to each other. Here are the two mirrors. And here comes my incoming beam. Now, if the angle of incidence must equal the angle of reflection, so I'll get a beam heading out in that direction. Angle of incidence, angle of reflection, which are equal. What's interesting here is if this is r, this angle here must be 90 minus r. Agreed? We know that all three of these must make 180, so that means 180 must minus the 90 degrees in the corner, minus the 90 minus the r, gives us 90 minus 90, and the minus minus gives us r, so that must be r. Therefore, this must be 90 minus r, etc., etc. This must be r, making this the incident. Now, I hope that hasn't confused you too much. Sorry, that must be 90 minus I, which is the same as r. Okay, that hasn't been too clearly explained. However, what I'm trying to say is that actually these two incoming rays, the incoming ray is actually parallel to the outgoing ray. Now, when does that become useful? Well, if you want a reflector, then all you need to do is you need to make a material which has, doesn't matter how small it is, these right angled edges. And if you can repeat that, this side being mirrors, then any possible light that comes in and strikes this surface will be thrown out directly at the same direction which it's come in at. Think about road signs. I'm not sure if you've been travelling at night and you've seen light striking a road sign, but suddenly the road sign flashes up brightly, whereas everything else hasn't done. It's because that the light that hits the road sign, doesn't matter what angle it's hitting it at, even at this very fine angle here, will always send the light back, so it will look brighter. Again, if we had a cube, and we imagine that this is the inside corner of a cube, then any beam that comes in will be thrown out. This is radar. So if you want a radar reflector to be noticed, for instance on boats, you haul up to the top one of these little cubes, internally facing cube, and suddenly any radar beam that comes in will be thrown directly back out again. They're really, really useful. Lots of the road signs, lots of the reflective materials that you wear if you're cycling late at night, or built into trainers if you're runners, or into the clothing if you're runners even, have very, very, very small versions of this which throw the light back out again. Okay, the next strange effect we're going to have is what would take place if, if we have this type of mirror. So now we're going to a con, I'll put that as the back. So it looks like a con, it's caving in, so this is a concave mirror. What happens if you've got a concave mirror? Let's throw in 3 beams of light and see if you can work out what on earth happens to these 3 beams of light. And I will set up as well here a convex mirror. And you can tell me, see if you can work out what happens with the 3 beams of light that go in. If you want to try, hit pause, otherwise here comes the answer. First of all, what we want to do is we need to make a reference point, the normal, to work out what's going to happen. So this is our normal set up at 90 degrees. and our normal here is actually at 90 degrees, and here it's at 90 degrees again, but because the surface is curved, these normals change. Then what we're going to have is we're going to have this beam heading in that direction. This beam strikes and goes straight back again. And this beam strikes and goes out in that the angle of incidence must equal the angle of reflection. Incidence must equal reflection. So suddenly what we're left with is a point of focus. So you're focusing the light. Okay, what's going to happen here? Well, interestingly, the normals, let's call it n, the middle one does the same, but the other ones face out. So what takes place? Well, the ray of light flies out in all directions away from it. Okay, so as long as you're able to work out reflection, simple reflection, which is easy, but as long as you're able to see the application of that, and as long as you're able to draw a simple object image and appreciate you have this lateral, let's put lateral inversion going on, then I think you'll have reflection sewn up.